Okay, so we're looking at the hemoglobin, and I abbreviate this with HB, oxygen dissociation curve. Okay, we're going to draw a similar graph here. We've got the partial pressure of oxygen on the left. That's in millimeters of mercury. On the x-axis, did I say on the left? I meant on the x. On the y-axis, sorry, we've got the percent hemoglobin oxygen saturation. And all that means is how many of those 4 oxygens are bound to hemoglobin. Right, so we've got 100%, got 75, 50, and then 25%. Okay, so we got 1, 2, 3, or 4 oxygens bound. And we talked about the shape of this graph being this sigmoid curve. Right, the sigmoidal curve. And that is really describing what we call cooperative binding. And cooperative binding means that oxygen binds more easily to hemoglobin after that first oxygen has bound. So after that first oxygen binds, we then have that steep rise in the curve, and then it flattens off. Okay? Now, we know that, so this is our first oxygen. We know that when we get to 75% oxygen saturation, this is the level of the partial pressure in our systemic veins, which is about 40 in terms of what we talked about last time, right? So at a partial pressure of 40 millimeters of mercury, we have bound 3 of our 4 oxygen molecules. Okay? And so this is a standard curve. So this is the way oxygen behaves, or hemoglobin behaves in terms of oxygen binding under normal conditions. What we're going to speak about now is when the curve shifts to the right and when the curve shifts to the left, and what are some factors that causes that. Okay, so let's describe the right shift first. So when the curve shifts to the right, hemoglobin has a lower affinity for oxygen, okay? It doesn't want to bind oxygen. It's going to unload oxygen easier, and it's going to load oxygen harder. So we've got a lower affinity. For oxygen, okay? Meaning that it's going to be harder to load oxygen and easier to unload oxygen. Okay? And we're going to talk about a lot of different states that align with this right shift, but we'll mention 2 things here now. This happens under the instance of increased body temperature, as well as increase in altitude. Okay, so increased body temperature, increase in altitude. And really, anytime we have increased metabolic activity, we have a right shift of this curve. Okay, So increased metabolic activity. And we can think about exercise as a really good example in that. Now, when the curve shifts to the left, we've got the opposite scenario here. So a left shift we have a higher affinity for oxygen, meaning that it is harder to unload oxygen. And it's going to be easier to load oxygen because of that increased affinity. This happens when we have decreased body temperature or when we have a decrease in altitude. Okay. All right, so I really want to explain why we have this right shift in terms of the big picture of what's happening. So the tissues are requiring more oxygen if we shift to the right. We're thinking about things like exercise, we're thinking about things like increased body temperature. We're going to talk about some other factors as we go on that shift the curve to the right. But if you kind of associate all of this with increased metabolic activity, then the other factors that we'll speak about will make a lot more sense, okay? And so what's really happening with this right shift is that we need a higher partial pressure. So a higher partial pressure of oxygen is required in order to fully saturate hemoglobin. So a higher partial pressure is required to saturate hemoglobin. Okay, so it's harder to get that oxygen to stay on hemoglobin. They don't have as much of an attraction or affiliation for each other, and that's kind of what we want in these types of scenarios. We want that oxygen to dissociate easily because these are instances when the tissue really needs oxygen, right? Increased metabolic activity, increased body temperature, even increased altitude. We know that at increased altitudes, we have what in terms of a partial pressure? Higher or lower? Lower, right? The higher we go, think about the top of Mount Everest, we've got a very low partial pressure. So we've got less available oxygen. So we don't want hemoglobin really affiliated or really binding tightly to oxygen. We want it to dissociate off easily. And so all of these instances align with that easy dissociation. At a left shift, this is the opposite, right? We can here afford to have oxygen binding tightly to hemoglobin because we just don't need it that much in the tissues. And so we need a lower partial pressure required to saturate hemoglobin here. Okay? All right, I hope that makes sense. And we're going to go on to speak about some other scenarios that shift this curve to the left and to the right.